In the chemistry lab, we make observations which are qualitative in nature, and these could include things like did a precipitate form? Was there a color change due to the reaction? Was the substance crystalline in nature? Anything that doesn't involve numbers is considered one of these qualitative observations. And then we also will be making quantitative measurements, which are measurements where we have a device that is going to give us a numerical value for some dimension or property of the substance. This discussion is primarily concerned with those quantitative measurements and how to correctly record them when we are making those types of measurements in the lab. When we are recording a quantitative observation, there are two things that we want to record. First is the number or the value that we get from our measuring device, and then the second is the unit that belongs with that value. Both of these are equally important, and we have to have both of them for the data to have meaning. When we are making measurements in the lab, there are two things we're concerned with. One is precision. We want repeated measurements of the same value to be very close to each other. And the other one is accuracy. Our goal is for our measurement to reflect the accepted value or the correct value of the thing that we're measuring. And so to look at the difference between these two factors, we've got several dartboards shown here, and we're going to make an analogy that the bullseye is going to be our true or accepted value, and then the darts are our measurements. In figure A, our darts are all scattered across the dartboard, and none of them are really very close to the bullseye. So in this case, we would consider that our measurements are not accurate because they're not near the bullseye, and they're not precise because they aren't near each other. In figure B, we see where we have all of our darts are fairly close to each other, but they still are not near the bullseye. So in this case, even though we're not accurate, we're not close to the bullseye, we still are fairly precise because our measurements are very close to each other. In real life, the way something like this might happen would be if you are making some sort of error in the way you're using a measuring device, and you are making that same error consistently. So your measurements would end up being very close to each other. However, because of the error, they're not going to be very accurate. In C, we see that all of our darts are much closer to the bullseye than before. However, they really aren't very close to each other. And so we do have a high level of accuracy in this case, but our precision is not very good. And then D is really where our ideal is, in that we have all of our measurements are close to each other and they are all accurate. They are all at the bullseye. Okay, so how do these two terms apply in real life? Well, basically, when we're making measurements in the lab, we really don't know what the true value is. We don't know if we're making a measurement, we don't know if it's accurate or not. And so we do repeated measurements and try to obtain measurements that are all close together. In doing this, we really do hope and assume that our measurements being close together implies that they are indeed accurate. But again, remember, this is still assuming that we are not making errors in the way we are making our measurement. Okay, when we record measured data, we want to write the numbers in a way that reflects how precise the measuring tool is. And so in order to do that, so that anyone that wasn't familiar with our procedure could look at it and get an idea of how precise our measuring devices were, we have these things that we call significant figures. And basically, significant figures is a way of recording data so that you are reflecting all of your known digits, which we're going to clarify here in just a minute, plus one uncertain or estimated digit. Okay, so let's look at using a ruler to measure the length of a cylinder. All right, in this case, our ruler is measuring in centimeters, and so we want to record the length of the cylinder in a way that reflects that our measuring device has marks for each centimeter, but also is incremented in a tenth of a centimeter as well. And so looking at this to measure it, we can see that it's definitely longer than 6 centimeters. So we know one of our known digits is the ones place. And then we also know that in the tenths place we have 1, 2, 3. So it's it's greater than 3, but then it might be, it just doesn't seem like, if we drew a line, it doesn't necessarily look like, that it's quite there to the 4. So we can say with certainty that it's 6.3 centimeters. But then we are allowed to estimate in between that smallest increment. And the way that we do that is by just sort of visually dividing the space between the marks into 10. And then trying to kind of estimate, well, about how far between those marks does this object that I'm measuring, how far does it go? Okay, and so you just kind of eyeball it, and this estimated digit or uncertain digit is called that because it's based on the opinion of or the expertise of the person that is using the measuring tool. And so if I were looking at this, I might say, well, it looks to me like it goes farther than halfway. And so maybe I might say, well, it's just a little bit more than halfway, so 6.36 centimeters. But then you might look at it and say, well, no, I think it's a little bit farther, and so I'm going to say 6.37. Okay, so both of them are correct recordings of the length of this cylinder. It has 3 significant figures because here are our 2 known ones. We have marks on our measuring device to tell us that it is greater than 6 centimeters and it is also greater than 6.3 centimeters. But then we have this last digit here that we are estimating because there are no marks in the hundredths place on this measuring device. Okay, similarly here we have a burette, and this burette has marks for every 1 milliliter. Okay, and then it also increments in a tenth of a milliliter. And so in looking at this, we would say that it's above 20, and it's above 20.1, which is right here. Okay, and then we would kind of look at the bottom of the meniscus, and to me, that looks like it's about halfway. So I would probably read that at 20.15 milliliters. Now you might look at it and say, well, no, I don't think it's quite halfway. And you might say, well, no, I think it's 20.14 milliliters. But either of those measurements would be perfectly valid.